Hello everyone. So I recently tried out this aeroacoustic resonance simulation. So when you travel in a car, at sometimes if you have lowered the window in the rear side, you might have heard of this kind of disturbing sound, air rushing in and out, and that's often called window buffeting. So that's an example of this Helmholtz resonance or aeroacoustic resonance. So I wanted to try it out and maybe create the sound using the simulation. Okay, so for that I did a small simulation. So and this was my geometry. So I have and this is the internal volume that I used as the domain. So you have this cavity, this rectangular or the square block region is the cavity, and you have a small opening to the outside. So assume this as your car cabin, and this is the external flow. Okay, so you have the inlet here, this is the inlet, and you have this one as the outlet, and rest of the faces I have defined it as a symmetric plane condition, and also applied a non-reflecting acoustic boundary type. Okay, so you have the pressure waves coming in and going out, and they can go through these walls. Okay, so my objective was to monitor the pressure inside this small cabin and see how that varies and if I can reproduce that annoying sound. Okay, so maybe I'll just brief through the simulation steps I did. You can find all the procedure in my previous videos, so just the peculiar things. Okay, so I can show you the mesh. So this is the section view of the mesh, this is the chamber, and you have the external flow here. Okay, so I used a trimmed cell measure for this case. Okay, then inside the physics I have used this acoustic wave model, which enables you to specify the boundary type using an acoustic specification which is non-reflecting. Okay, so the pressure waves doesn't reflect back at these boundaries. Okay, so which is like open to atmosphere. Okay, then you have a slip wall, which is maybe you can consider it as the surface of a car perhaps, and you can find similar situations like cavity oscillations, or if you consider an aircraft, it has a lot of bays underneath the fuselage, and whenever they open they can also induce this cavity driven oscillations, and if these oscillations go to resonance and have a high frequency, um, they can be sensitive to equipments inside. Okay, so you can use such simulations to study about how the geometry actually causes the oscillations, and also what will be the frequency of oscillation at some particular airspeed, something like that. Okay, so that's the boundary conditions that I used, and I used the time steps settings as like 1 millisecond, and you have this acoustic wave solver. Then I have used the average pressure inside this chamber as a monitoring value for convergence. So since I start the simulation, there will be a stage or the initial time period where the simulation is not yet stable or converged. When you have a converged situation, you will have a fixed amplitude of the pressure wave. Okay, or the pressure cycle will be something like a periodic cycle. Okay, so there is this transient period and you have this steady oscillating period. So by monitoring this pressure inside, you can actually know if it's reached that steady period or is it still progressing. Okay, and I have used some scenes. So this is the pressure scene. So inside you have the um, chamber, and you can see these pressure contours like waves. Okay, so it's kind of bounce back and forth like a like you say, you can say your eardrum oscillates to sound like this. So it's the same procedure. So you have the ear, you have the cavity, and you have a diaphragm inside. So whenever the sound waves come, it vibrates, something like that. When you have this cavity and the flow, there is this shear layer between the stagnant region and the outside flow, and the air kind of moves in and moves out, and that motion kind of oscillates and goes like a tapping in a periodic way. Okay, so that pressure oscillations create the sound wave, or that annoying noise we usually hear. Okay, so I have ran the simulation and until 8 seconds of physical time, and this is the residual plot, uh, and I have recorded the scenes, and I will show you the results. Okay, so I have stitched the scenes captured using the Python script which I usually use. Then you can see the average pressure plot inside. So again, as I mentioned, I have skipped the transient time. So until first 2 seconds of physical time, the plots, everything is from 2 seconds to until 8 seconds of physical time since the start of the simulation. Okay, so this one here, on the bottom right you have the pressure contour, and on the bottom left you have the velocity vector field, and on top you have the average pressure variation plot. So as you can see in this pressure contour plot, you can actually see uh, the pressure oscillations at the opening. So it kinds of go back and forth like in a cycle. Okay, and also in the vector plot you can see kind of air moving in and out, and if you can see this pattern of small uh, velocity vectors caused by the pressure fluctuations. Yeah, it looks cool. In the pressure plot you can actually see right now the variations are starting to feel like they settle, in the sense that oscillations are more periodic and steady, and you have so many modes in between. Okay, yeah, so using this pressure wave, I actually recreated the sound using ChatGPT helped me with the code. You created a small Python script to convert it into a sound wave, adjust the um, loudness of it. Okay, so my cavity is not in the scale of a car, it's a small cabin like 1 feet cube. Okay, so my sound amplitude and all was low, so I did some tweaking on increasing the intensity of the sound, and I managed to get um, that annoying sound. So I can play it. Okay, and also you can see this isosurface of pressure fluctuating with the annoying noise. Okay, it kind of helps you to visualize like a diaphragm. Okay, so that was physical 8 seconds. I found it cool to try out. Well, I always wanted to generate sound from a simulation, and this is the first time I actually tried it out. So that was fun. Thanks for watching.